Hello everyone and welcome to the fifth lecture of the course Advanced Structural Analysis. This is the last lecture of the week 1 and we will try to give the idea of the energy concept and the virtual work principle through this session. These are the brief contents which we will cover through this session: that introduction to the energy concept, the real and the virtual strain energy in the structural analysis system, and then we will try to discuss the real work principle for the given systems. So, as we have already seen the methods of the slope and deflection, one primary point which we considered, the basic assumption which we made there was that the system was considered to be a flexural system, which means that a system which is subjected to pure flexural forces, we can accommodate the standard methods of the double integration, the conjugate beam or the moment area in those cases. At the same time, when it comes to the given problems with respect to the simplistic generalization, those methods can be accommodated or they can be easily used for the given cases. But as the system becomes more complex and at the same time the effect of the other deformations of the system, including the shear deformation, the contribution of the twisting deformations in the given system, as they become significant, we need a more comprehensive approach which can accommodate the deformations due to all the possible deformations in the given system, and at the same time which is more comprehensive and accessible to the generalized systems. And in this regard, we come up with the method which is called as the energy approach or the energy concept in the structural mechanics. Now, as a basic principle of the given system, we consider that any external work done by the given system of the forces in the given structural system will be translated into an equal amount of the internal stored energy of the given problem. Of course, while we are doing this kind of a equivalence, we are considering the system to be a conservative system, which means that there is no loss of the energy which is taking place. Any kind of a dissipative systems where, say, the heating of the system, any kind of a system where some kind of a loss due to the damping or other criteria are being taking place, those systems are not considered in it. But a system where any kind of a loss is not taking and we consider that as a conservative system, we simply define that amount of the external work done by the forces is equivalent to the internal stored energy of the given system. And now, balancing these two components, we can easily get a basic rule which can consider the standard conditions of the slope and deflections of the given system. Now, to identify this, we also come up with the concept of the total potential energy of the given system. We will try to briefly look into it, that how that translate into the idea of the general equilibrium and the compatibility conditions of the given system. To understand, first we come up with the strain energy of the given system. So, as we said that we are trying to correlate the external work done by the given system in terms of the amount of the internal strain energy associated. So, we want to first define the strain energy associated with the given system. If we talk about the strain energy, we understand as a simple measure, if I do a tension test on a given bar, we can draw a simple stress strain curve for the given problem, and now the general stress strain curve which is drawn for the given problem, the area under this curve is typical measure of the strain energy associated with the given problem. So, in general, we can define the strain energy of the given system as the integral of stress into strain over the total volume of the given system. Now, the idea of doing it as a volume integral is based upon the understanding that the stress is having a unit of the Newton per square meter, the strain is unitless. So, if I want to come with the definition which is the energy units, I have to do the integral over the total volume. So, the sigma into epsilon is a typical representation of the energy over the unit volume of the given system. It is also defined as the strain energy density of the given system, and now to define the overall energy, I have to do the volume integral. As we have already come up with the system that in a generalized problem, we do not have only one measure of the stress, but we define the stress as the representative value with respect to the 9 number of components, out of which the 6 number of components are at least independent, because these components are defined with respect to the individual values, whereas the off diagonal these terms can be considered same as the terms which are represented with their respective counterparts using the simple condition of the shear balance. Based upon this idea, if I want to define the strain energy associated with the given system for all these stress components, one has to define it that this representation will be written for each measure of the stress and strain in the given system, and one can simply define this with respect to all the corresponding values of, so if we just briefly write for all the components, I can define it in the manner of the stress and the strain representation of the given system over the total volume integral. As we define the total 6 number of independent values of these stresses, so rather than taking them all in the matrix form, we typically define these values in a standard vector form, where the idea of the independent stresses sigma x, sigma y, sigma z, the tau of xy, tau of xz and tau of yz is defined for the given problem. One must understand that by writing these stress measures in the vector does not mean that it is a vector by definition. A given arrangement is just arranged in the form of an array, so that I can easily understand that these are the 6 values which are independent values of the given system. I can define this as a simple representation of the sigma, which means that this is the measure of all these 6 values of the stresses. In the same manner, I can define the strain also in the similar manner, and these 6 corresponding strain measures of the given system can be identified. So now the same expression of the strain energy, which is expended in this form for all the 6 values one by one, can be written in a more comprehensive manner by the vector summation, and that can be defined as epsilon transpose sigma into dV. So one can understand that as a simple metric size, sigma is having 6 number of components, sorry, epsilon is having 6 number of components, sigma is also having 6 number of components in the given system. So their sizes are 6 cross 1, and if I want to consider the matrix multiplication to give the energy, which is a scalar quantity of the given system, I have to consider the multiplication by the formal rule of the matrix multiplication. Sigma being 6 cross 1 can only be multiplied with some system of the strain which is in the order of 1 cross 6, and that is where I have to put the transpose of the strain component in the given system. So this is the general idea how we define the strain measures, strain energy measure of a given system. But as we have already understood also in the previous session, that in a general structural mechanics, we do not go with the values of the stresses, but rather we have identified that we will be defining some values of the stress resultants in the given system. So we have Nx, we have V of y, V of z, then we have the moments in the given system which are represented as the stress resultants of the given system. So now rather than defining the values of the stresses in the given system, we define the stress resultants of the given problem, and we also define their corresponding values of the stress measure of the given system. So as we are defining with the given system of the axial thrust Nx in the given problem, we are interested to define the corresponding value of the axial deformation Ex in the given problem. If I am interested to define V of y, which is the shear force in the direction y of the given system, I am also willing to define now the shear deformation E of Sy in the given system. Similarly, we have defined all the components of the deformations of the given system. We have defined the components of the stress resultants also of the deformation system. So now if I represent them as a simple rule of some stress resultant F, and the corresponding values of the deformations are defined by the E, I can draw a simple curve between the stress resultants and the corresponding values of the deformations, and the area under this curve will also give me the measure of the strain energy for the given system. So the understanding is that the stress and the strain, which is represented for the general continuum in the system, has been reduced to a simple problem of the stress resultants and the corresponding deformations to define the strain energy. And this way we are able to define the strain energy with respect to all of these components of the given system. Now as we come up with the general idea of the stress resultant of the given system and the corresponding deformations, we now define that how to consider the strain energy of the given system for all the cases. As a simple representation, we have say considered the small change from f of I to del of f of I, which is taking place on the given system with respect to the excess of the stress resultant. With respect to the deformation, we are having a small change which is taking place from E of I to the E of I plus delta of Ei in the given system. Now I can consider this area under the curve, which is shown by the blue region in the given system, and I can represent this as the measure of the strain energy, and that is defined as the multiplier of the stress resultant, which is f of I. I have considered that over this total domain, the measure of the stress resultant is more or less constant, and I have only change being taken place with respect to the deformation of the given system. So that is why we multiply f of I into the strain or the change in the deformation of the given system, and that gives us the strain energy measure of the given system. One must also understand that as we have already converted the given stresses into the stress resultant, now one is not required to do the volume integral of the given system. It is a simple idea which can be considered that when we were writing earlier stress into strain as a volume measure, we were considering the stress as a representation of the overall unit area of the given system, whereas strain was considered as a unitless quantity. Whereas now when we consider the resultant force and the corresponding displacement, we consider that this value is the representation of the direct force, which is in newtons, and this value is the measure of the displacement, and this could be defined in terms of the meter of the given system. Of course, when it comes to the moment, the force will become in the value of the Newton meter, whereas the displacement will become the rotation of the given system, which will be in the radian, and that is why we will not be able to include the volume integral in the given system. It will not be required. So with this idea in mind, we have defined the strain energy as a area under this curve, where we have defined the corresponding stress resultant and corresponding changes taking place over the given deformation. One can also consider the area which is covered by this red region over here, and that is typically called as the complementary strain energy of the given system. One can consider that physically this representation has no meaning, but at the same time when it comes to the nonlinear system, this mathematical representation becomes much more helpful, and that is why we can identify the complementary strain energy associated with the given system by including the strain or the deformation measure being constant, whereas the force measure or the stress resultant measure being variable or undergoing any small change of delta Fi. So with respect to that, we can define the complementary strain energy associated with the given system. This particular process can be done for all the components of the given system. So if we are talking about, say, a frame problem, we have multiple of the members, say member 1, member 2, member 3 in the given system, and this integral will be done for all these members one by one, and that is why we define that this has to be added for I equal to n, where n defines the total number of members in the given system. At the same time, this f of I is represented at this moment for only one particular stress resultant component. So either it could be with respect to axial, or it could be with respect to the shear in the given system, or it could be with respect to the moment in the given system, and we have corresponding deformation of the given problem. But as we consider the overall generalization, we can add all those components together and define the net strain energy associated with the given system. As a next case, in most of the problems which we deal in the structural analysis of the civil engineering utilities, as well as the general mechanical and aerospace system, where we need to analyze the systems for initial loading profiles, we consider that the systems are active within the linear range of their material deformation, and in those conditions the stress strain profile or the load deformation profile with respect to the stress resultant and the deformation can be considered to be linear. And once the system is considered to be linear, I can evaluate this area under the curve by the simple measure that the value of the force which is active in the given system, say f of I, and the corresponding value of the total deformation which is defined for the system, say E of I, and then this area under the curve which is defined by the triangular region, and this is the area half of f of I into E of I. So this is the simple representation for a linearly elastic systems, where the value of the strain energy with respect to the given stress resultant and the deformation can be easily calculated as the area of this triangular region. Now we will try to move with different components of the stress resultant, starting with the first case where we have an axial strain energy of the given system. So we have, say, considered a simple problem having a simple axial force or the axial thrust n of x active over it. Corresponding to it, we have already calculated the deformations in the earlier lectures, which comes out as E of x equal to nx dx upon AE. So now if I want to calculate the amount of the strain energy for a linearly elastic system, I can define it as half n of x, which is the stress resultant, into the E of x for the given system, and it comes out as nx square dx upon AE. So this is the value of the stress resultant and the strain measure or the deformation of the given system being multiplied, and this comes out as the axial strain energy of the given system. We can consider now in the similar manner the component of the strain energy for different other deformation profiles of the given system. So if we now go with the truss members, we understand that the truss members are actually deformable members. So the same formula which we derived earlier is valid for those given systems. Now only difference is, In a truss member, internally the member forces do not change. If I say that the member is having a force at the end of it as a n of x, the internal member over here or any other point of the system will have the same force n of x. The force does not vary with the length in the given system, and that is why the original expression which we derived over here can simply be considered that nx is constant all throughout the length of the given system. So this expression is not only valid over a small length, but I can idealize it to the overall length L of the given system, and that is why we can simply do it as half n square L upon 2 of E. And now we can do this integral, we can do this summation for all the members of the trusses from 1 to m number of members, and this will give us the total axial strain energy associated with the truss members. In the same manner, if we go to the flexural system, this is the flexural strain energy which is defined. With respect to this, now I can define the flexural strain energy can be included as half of the amount of the moment in the given system into the d theta which we have defined over here, and with that we get the expression of the given system like this. This is the general expression which we define over a small length of the given system x. As I am doing this integral over the total length, we have done this integral for the length 0 to L of the given system. I can do similarly for the shear deformation and the twisting deformation of the given system, and this is the total energy component which can be evaluated for the shear and the twisting components of the given system. Now, once we are comfortable with analyzing these all strain energy components, one can define the total net energy of the given system, which is associated with any given structural system, is the summation of the axial, the summation of the bending or the flexural system, plus the shear system of the given problem, plus the twisting of the given system. So, the summation of all these energy components together will define the net strain energy associated with the given problem. In most of the problems of the beam frames in general, we typically consider that the bending energies become significantly larger, and that is why we typically introduce that the other components of the energy are relatively smaller. We will see that in the subsequent sessions with few examples as well. Now, as a second case, we typically identify that the strain energy of the given system is equivalent to the external work done by the given forces. If we consider a simple system like this, which has multiple of the forces active on top of it, these are all the external loads. To define the external work done corresponding to any force, we have to define the corresponding displacement in the direction of the force. And with this expression, as we have multiple of the forces, we can define the corresponding displacement in the direction of each of these forces to define the net work done by the given system. So, the work done by the given force P of m will be equal to P of m into delta m, and this will be considered with respect to the given representation of the small change in the delta m which is taking place, and as I will integrate it over the total length of the given system over the change of the deformation which is taking place in the given system, I will be able to calculate the net work done by the given system. So, I can define in general the expression that the external work done or any change in the work done of the given system is equal to the number of force systems which are active in the given system. The summation is being done for all of them, and P of I into delta I of the given system, where delta I represents the any small change. So, delta m, delta 3, delta 2, delta m, these are the final deformations associated with the given problem. But as we are trying to evaluate these expressions, we will calculate that the system moves from one position to the next, and there is a small change taking place which is of delta 1 over here, say delta 2 over here, and these are the small finite changes which are described for the given problem. And corresponding to that, we have calculated that with respect to the external load, these are the small changes taking place. So, the total change in the external work done is equal to defined by this part. Now, if I do the similar process as a overall system, I can do this as a simple integral, the total work done, and that can be described from the position of 0 to the net displacement delta 1 taking place over the given system. As we understand that if this deformation which is taking place in the system is again in a linear range, that means the system is following a simple linear distribution for the load and displacement, I can calculate the work done as a simple area under the given curve, which is again a triangular profile, and that gives me a factor of half in the given system. So, a real work done of the given system for a linearly elastic system can be identified with a factor of half, which typically can be understood by the simple idea that the original load of the P1 is responsible for making the system to undergo a deformation of delta 1, which is starting from the initial value of 0 and reaching finally to the delta 1 value of the given system. So, all throughout the given deformation taking place in the system, we consider the average value of the load, and that considers somewhere as P1 by 2 for the given problem, multiplying it with the net deformation taking place over here, which is delta 1. Similarly, I can do it with respect to P2, the average force P2 by 2 into delta 2, and subsequently for all the remaining cases, and that constitute the total work done of the given system. As we have defined this particular work done for the given system, now we can equate it with respect to the external this external work done with the internal stored energy of the given system, and that will give us the basic principle of the real work. So, to define this, we simply consider that the work done by the external loads is now equivalent to the changes which are taking place in the internal strain energy of the given system. So, we have already calculated the work done by the external load as the W. The internal strain energy of the given system is also calculated, which is defined as U, and now we equate both of these parameters of the given system. Interestingly, we can consider that the net potential energy associated with the given system is the summation of these two processes, where we have the work done by the external load as well as the internal reactions of the given system, because the internal strain energy can be considered that it is the internal work done by the given system. Of course, there is a primary difference. When we come to the external work done, we have a load which is active on the given system, and the displacements are also taking place in the same direction of the given loads. So, the measure of the work done for the external system is positive, whereas when it comes to the internal strain energy, we have a system which is undergoing some deformation, and due to these deformation the system is generating some internal resistance. So, if we define the E of x as the deformation in the axial direction, the measure corresponding to it of the stress resultant is opposite to it, that is trying to resist this change, and that is why this measure is negative in the given system. And with this idea, if we add the total potential energy as U plus W, we consider that U is actually minus of U with respect to the given expression which we have defined, because it is corresponding to the changes which are taking place in the given system, and these internal stresses are trying to resist these changes of the given system. And by equating these two, of course, if we say that the net potential energy of the given system is 0, the U is equal to W, and that gives us the expression of the given work done in the given system is equal to the internal strain energy associated with the given problem. This is the standard problem which we defined and which we will try to see in the subsequent few sessions to calculate some of the standard solutions of the given problem. Now, at the same time, a very natural problem occurs in the given cases of the external work done, and that is, if the load which we are providing to the external system is not active at the same position where I am trying to define the displacement. If I say I want to evaluate the displacement at this position, whereas the load is active at some different position of the given system. Now, if I consider the work done, I cannot multiply P with this value of delta, because as I understand, this expression is not correct, because the load is active at a different position and the displacement is active at a different position. To understand now, or to tackle this kind of a problem, what we consider, we come up with the similar system, a system like this. We understand that the displacement which is taking place, so if I just define these points as point C and D of the given system, we understand that we are looking for the displacement at the point D, but as there is no load active at that point directly, we will apply some virtual load. We will bring some dummy load on the given system, and we will say that, let's say that there is a virtual load of the given system P star active there. Of course, P star is not the actual reason for this given displacement. The displacement which is taking place in the given problem is primarily due to the load P, and that is why we call P star as a virtual load. It's a load which is just provided virtually in the given system to accommodate the position of the work done. And now, as we consider the given system, to evaluate the work done corresponding to this virtual load, we can simply say that work done due to this load will be equal to the amount of the load P star into the corresponding displacement which is actually taking place in the original problem, and that is delta of the given problem. The understanding over here is that we have not used the factor of half which we were earlier using in the given problem, and this could be understood because as the P star is not responsible for making this deformation delta over here, so I don't need to add the half factor for the given system. If one want to graphically represent it, I can draw the distribution between P star and delta. As the displacement is changing or increasing in the given system, I understand that the P star is having no effect on this, and that is why the P star is more or less constant all throughout this given process. So area under the curve can simply be considered as a simple rectangular area of the system, and that is considered as W equal to P star into delta. And with this concept in mind, we now come up with the thought that in cases where the load is not directly active at the position of the displacement, the consideration of the virtual load can be made, and with respect to the virtual load, we can define now the external work done with this parameter. And as we have defined the virtual load in the given problem and corresponding to it we have the virtual work done, correspondingly I will also define the strain energy measure of the given system. So we will put this star sign with the work as well as the energy concept, which will make that now this is the virtual work done by the given problem, and this U star is also the virtual strain energy associated with the given problem. So we call it as virtual strain energy, and in order to define this virtual strain energy associated with the given problem, I will now not include the factor of half. I will simply define the F of I, and as the loading contribution or the stress resultant contribution is due to the virtual part, I will also put in this the Fi star component in the given system, and the corresponding value of the deformation which is taking place, that will be provided with respect to the real system. So this is with respect to the real system, whereas this component is with respect to the virtual system. So this is the virtual system which we have defined with the application of the dummy load, whereas this is the real system in which we are calculating the displacement with respect to the actual load active on the given problem. Now with this idea, we will try to take up few problems in the given cases, and we will see that if we have the given system which is originally defined as the real system, we can describe the moment distribution over here. This moment distribution appears as M, whereas in the virtual system if I define the moment distribution, it appears as a M star in the given problem. Now if I calculate the work done for the given system, I can write the work done as P star, which is the virtual load, into the displacement which I want in the original system, which is delta. Now if I want to calculate the virtual strain energy of the given system, I will write it as this is equal to the F star, which is with respect to the bending component. So I will write it as M star in the given problem. So the moment distribution will be defined with respect to the component of the virtual system multiplied with the d theta in the given problem, and the d theta will be defined with respect to the real system of the given problem, and this can be described as M star into, now d theta we define in general as a simple expression M into dx upon EI, and this gives us that the U star is equal to M star M dx upon EI. So if you can recall, earlier when we were doing this problem, we defined the problem of the work done with respect to the given real system as half P into delta for the given problem, and the real strain energy associated with the given problem was defined as half M square dx upon EI. Now in the given case, if I am going with the virtual work, we have this given system as half P star delta, where P star is a virtual load, and similarly the U star, which is the virtual strain energy, also includes the moment distribution with respect to the virtual system. So this way we are able to now give a principle which is not based upon the real work and the real strain energy, but which is the equivalence of the virtual work and the virtual strain energy of the given system. With this we stop over here. We have briefly discussed the energy approach and its utility in the structural mechanics. If now one can see the Castigliano's theorem, which are typically discussed in the basic courses, one can correlate it with the principle of the strain energy also, and then we can now see that the standard slope and deflections can be calculated using the strain energy concept, and this will not only limit us only to the flexural system, but we can also include the system with the shear and the other related effects. With this we stop over here. These are the components of some of the references which have been used during the first week of the lecture. One of the book with the theory of structures, you can refer the chapter 1 and 2. Some of the problems are also there which can be tackled. At the same time, the standard reference books which have been defined in the course that can be used. The chapter 1 in that introduces these basic concepts, and you have a multiple of the problems also available in that. So we stop over here. Thank you everyone.